So our today's lecture, so last time when we spoke about symplectic geometry, symplectic manifolds, and the ultimate theorem about symplectic manifolds, well, unless you go further into details, into some new developments like Gromov's squeezable property, I don't know, capacity of symplectic manifolds and other things like that, unless you go into this really modern and interesting stuff. That's actually the top theorem about symplectic structures is Darboux theorem. Let me recall Darboux theorem. So for every symplectic manifold M, with symplectic structure omega, and for every point x in M, there exists an open neighborhood ux of x, and coordinate system on ux, x1, x to m, x to n, such that the restriction of omega to ux will be presented will be equal to the standard symplectic structure in these chosen coordinates. These coordinates are called Darboux coordinates, and unfortunately we have no control over how they appear, how they emerge. This Darboux theorem, whatever construction you use, whether it is a classical construction which gives you the coordinate system by iterative solutions of differential equations and so on, or whether you use the Moses streak that I explained to you last time. In any case, this construction only, this theorem is just the existence theorem, right? We have no, hand-on control over the behavior of Darboux coordinates. However, the existence of Darboux coordinates is important for many applications, and next time, well, not next time, but probably in the near future, comparatively near future, we'll see how the deformation quantization problem is simpler in the symplectic case than it is in the case of generic Poisson manifold. So when I say Poisson, I mean that even when M is equal to Euclidean space, or more generally, not even, but any dimension, even in that case, we need not write this symplectic form in in this way. I mean, even in that case, you can write the form, or probably better to write the bivector field pi, which corresponds to the inverse of the form omega. For instance, like this. To P needs not be equal to n. In fact, it should be less or equal to n. So this is a very natural example of some bidifferential operator, some bivector field, which exists on Euclidean space, but which cannot be obtained as an inverse, as the inverse of some symplectic form. However, in this case, we still have the model product. The model product still is applicable, and it gives you a star product on the algebra of functions on R to n, or Rn, are probably extended by formal parameter. So it is time to incorporate this generic case into the general theory. That is to say, go from Euclidean space to some curvilinear surface to manifold of certain dimension. And that brings us to the following definition. One says that a manifold M, so let M be a smooth manifold, one says that M is equipped with a Poisson structure if we have a Poisson bracket on M, on the functions on M. If we are given a bracket from tensor square of functions on M to the functions on M. And this bracket should verify the standard identities. So first, such that first, the bracket of f and g is equal to minus the bracket of g and f. Now we have this standard skew symmetry condition. Number two, we have Leibniz rule. For any three functions f, g, and h, we have the equation f comma gh is equal to f comma g times h plus g times f comma h. And the third, the last but not the least condition is the Jacobi identity. So let us, so this is the usual way to describe the Poisson structure. And of course, manifolds with Poisson structures, they give you a natural category of manifolds, right? If you have two manifolds, M with some Poisson structure on it, and N with some other Poisson structure on it, one can define the map, the Poisson morphism from one to another as a smooth map f from M to N, such that for any two functions on N, their pullbacks with respect to f capital will Poisson commute precisely as the pullback of the Poisson bracket on N, and so on. So this definition is actually quite nice. You can define products of Poisson structures and so on and so forth. They have actually, I think nowadays there even exists a whole new branch of mathematics called Poisson geometry, the study of various aspects of Poisson structures on smooth manifolds. Just like symplectic geometry is the study of various properties of symplectic structures on manifolds. However, in our case, we'll not go deep into this science, into this theory. We'll just describe the basic properties of Poisson manifolds. But probably I'll begin with some examples. Of course, the first and the simplest example is, well, Rn with constant by vector field. In that case, Poisson bracket of f and g with respect to pi will be given by the formula which you already encountered when we spoke about the model product, will be equal to pi ij df dxi times dg dxj. Here pi ij is our coefficients of the matrix pi, so they're antisymmetric and they're constant. Well, complex or real doesn't matter. The first condition holds automatically because the sign changes when we change the indices here. The second condition holds also automatically just because the partial derivatives verify Leibniz rule, nothing else. And as far as the Jacobi identity is concerned, well, it's a little bit trickier, but we can actually do the following thing. We know from linear algebra that every antisymmetric matrix can be brought to the standard form in some basis. Sorry, I think one is here, minus one is here. It's actually not very important, but I think it should be like this. And then there will be zeros in the end, right? So every antisymmetric matrix can be brought to this form in some basis. Hence, since these coefficients are constant, right, we can actually do this linear change of coordinates in Rn, and that will actually bring this formula into the standard one. You see, since this linear change of coordinates with respect to some constant matrix, these constant coefficients emerge from these partial derivatives and interact with pi ij. So we just get the formula that f comma g with respect to pi is equal in this new coordinate system to just the sum df dpi dg dqi minus df dqi dg dpi sum for I from 1 to some p, so that 2p is less than n, less or equal to n, actually, right? But in this case, we already know that the Jacobi identity holds just from the very first lecture, right? So this is the first example. The second example is quite evident also. It is the case when the Poisson structure appears from the symplectic structure, from some symplectic structure. So we have some symplectic manifold, and omega and we take pi equal to the inverse of the symplectic form, in that case, we already know that all these conditions hold. Well, I mean, hold if we take pi, take the bracket of f and g equal to pi applied to df dg. So that's just something we already know. And here is a third example. Now suppose that G is a Lie algebra. Let G be a Lie algebra. Let G be a Lie algebra. I hope you know what Lie algebras are. I just don't know if you have already attended some course on Lie theory or not. Okay. So suppose G be a Lie algebra. In that case, we take M equal to the dual space of G. We can now do the following thing.
So it's a linear function, right?
No. Oh, yeah. I mean this. Yeah, this is the space of linear functionals. Phi G, two numbers, phi linear. Everything is finite dimensional, by the way, of course. So what we do further? Let now f and g be two functions on g star. Okay, g check. I don't know how to call this. Check, v, not star. Okay. Then the differentials, they are sections of the dual, of the cotangent bundle of g star, so g check, right? So for every x, for every phi, let it be phi, in g check, the value belongs to the dual space at phi of g check, which you naturally identify with g, right? Because double dual space is equal to the original space in finite dimensional case, naturally, right? For every point phi. So when we have two functions, the same is of course true for g, right? So we have, for every phi, we have two vectors in g. And we just put the bracket of f and g at point phi to be equal to the value of phi, a linear function on the commutator of d phi f and d phi g. So that's what I sometimes call the standard Poisson-Lie structure, or Lie Poisson. There is a subtle difference between Poisson-Lie and Lie Poisson. I think this is Lie Poisson. Okay, the standard Lie Poisson structure, and in many textbooks this is called by the names of three authors who actually brought to attention this structure for the first time. This structure has been known for sure to Sophus Lie himself, but the structure bears the names of Kirillov, Alexander Kirillov, yes, Constant, Bertram Constant, and the third guy, I don't remember his name, Studio, yeah, but I don't remember the name. Is he Jean or Jacques? I don't remember. I think like this. In French names, you can always add few vowels and then safely, something like that. So let us prove that this is indeed a Poisson structure. It's not very hard, so let us do this. So first, the skew symmetricity is evident, right? Nothing actually prevents it from being skew symmetric, right? The Lie bracket is anti-symmetric, so it's skew symmetric. Also, the Leibniz rule follows directly from the fact that the differential verifies the Leibniz rule. So Leibniz rule and skew symmetry follows immediately. 1 and 2. So conditions 1 and 2 are evident. Now, as far as the Jacobi identity is concerned, so there are a few ways you can do it. Let us do it first in some abstract way. So when I have F, G, and H, and we compute it at some point phi, it is equal to phi applied to D at phi of the Poisson bracket at F and G, right? And D at phi of H. But what is D? Oh, sorry, I forgot the second bracket. But what is D? What is differential of this function? It is just equal to, since this is linear in phi, this bracket is just equal, the differential of this function is just equal to this bracket. So what we have is just phi of this combination, d phi f, d phi g, d phi h. And now the Jacobi identity follows directly from the Jacobi identity for the Lie bracket, right? And Lie bracket verifies Jacobi identity. So that's how you do this in an abstract way. That's not very hard. But I think it is probably interesting to look into the coordinate way of reasoning, because physicists often like coordinates, often prefer coordinates. And probably it is nice for you, it would be nice for you to see the coordinates here. So we choose basis, the basis x1 through xn in G, right? So we have the following equation, which actually depicts the Lie bracket in terms of these bases. For every xi and xj, the right-hand side can be again expanded in terms of the same basis. So ci, j, k are the coefficients of this expansion. We have this equation. Yeah, they're called structure constants. Okay, let us look onto this formula more attentively now. First of all, x1 through xn can be now interpreted as functions on G star. Oh, sorry, G check. I quite forgot. I prefer this now. Okay. So they are functions. Actually, they are coordinate functions. So, what is d phi of f? It is equal to, it is just a vector, kind of. It's just the collection of partial derivatives of f with respect to these coordinates. So it's just something like this: df dx1, df dxn. Right? You can actually imagine that they are just coefficients standing in front of x1 through xn. So you can actually write it as sum df dxi times xi, where here xi in this formula, they are just the coordinates, and here they are bases. So they look the same, but they're different. So we write this formula in terms of the coordinates. So what is it equal to? So first of all, it should be phi applied to the bracket of df dxi xi dg dxj xj. And of course, the values here are taken at phi, and the bracket is taken in the sense of this formula, right? So what we get is phi applied to C sum over I, j, and k df dxi dg dxj xk, right? Now, these are just some coefficients. All these part are just some coefficients. They're just numbers. But when we apply phi to a vector xk, we obtain just the kth coordinate of phi, nothing else. So again, abusing a little bit of notation, we obtain the following formula. Xk probably of phi times Cijk df dxi of phi dg dxj of phi. So this is the formula. As you see, here are the coefficients of pi. They are pi. Well, it's natural to write these coefficients with upper indices. However, here they appear with lower indices, and that's because we work on a joint space, not on the original space. But that's actually very small, trouble. As you see, they are not constant. They actually depend on the point in our dual space. And hence, even if Cijk are so good that they give you some symplectic structure in a generic point, so they are non-degenerate in a generic point, still, you can, by changing the point, you see that this structure is in fact Poisson, generic Poisson. It's not symplectic. And these functions are linear in x, k, so hence non-constant. Non-constant. Okay, let us now prove finally that by direct computation, I think it's a good exercise from pedagogical point of view, that these coefficients verify the Leibniz rule. And to this end, we just do the following thing. First, sorry, not Leibniz rule, verify the Jacobi identity. Jacobi identity. First, we write down the Jacobi identity for the Lie bracket. As you see, it means the following. You take xi, xj, and commute the commutator with xk. On one hand, it should, and then sum this up over the cyclic permutations of I, j, and k. On the other hand, if you write this down in coordinates, you'll see that it is equal to c I j k c k cp p k q xq, right? Now you add cyclic permutations. So you get C, P, J, K, C, P, I, Q, XQ, plus C, K, I, P, C, P, J, Q, XQ. And it should be equal to 0, and that means that the sum of these indices, C, I, J, P, C, P, K, Q, plus C, J, K, P, C, P, I, Q, plus C, K, I, P, C, P, J, Q, is equal to 0 for all I, J, K, and Q. Right. Now we return here and try to write down the coefficients of the double Poisson bracket. Sorry, of the Jacobi identity. I leave it for a while without proof that the only coefficients which will survive eventually are coefficients which contain first partial derivatives of f, g, and h in the formula. So I will concentrate on this. So when we have this in h, it will give us what? It will give us c, I, j, k, xk, df, dxi, dg, dxj, comma, h. And again, I tell you that the only things which will survive are the terms with linear partial derivatives, first partial derivatives in f, g, and h. I'll prove this later, just a little bit later. So what we have looks like this. It will be equal to C, I, J, K, C, K, P, Q, df, dxi, dg, dxj, dh, dxq times x, sorry, not q, x, sorry, xp. And here we have xq. Right? As you see, we have precisely this sum, which in the Jacobi identity, and it vanishes identically. So we proved this by direct computation. The only thing which remains not quite explained is the condition that only first partial derivatives of every term survive. Because you see, when you just apply the formula like this to this expression, you eventually get partial derivatives, second partial derivatives of f and g, right? So why do these quadratic terms disappear? For what reason? I'll explain it a little bit later. Actually, I'm going to explain it, well, in 5 minutes. But before that, I need to develop some small theory. Yes, okay. I need to develop some theory, some very natural and simple theory. Right, it respects linearity in some sense. Okay. So, definition, which I already gave you a few times, but this is the first official time I give it to you. So this definition. Let M be a smooth manifold then polyvector fields, P polyvector fields, P vector or P polyvector, or just polyvector fields on degree P are sections alpha of the tangent of the pth exterior power of the tangent bundle of M. So you are used to dealing with sections of exterior powers of cotangent bundle of X, of M, right? They are called differential forms. And they're quite useful in differential geometry, right? They're used widely in differential geometry. It is strange that the dual counterparts, the sections of exterior powers of tangent bundle, are not that widely known by an average student of mathematics or physics. However, they're quite natural. You can define them in precisely the same way as you define differential forms. Locally, alphas, such polyvector fields, are represented by the formulas like sum over all multi-indices i's, say right, something like that. Alpha sub I of x d x I1 dx in ip, where d1 through dn are the basis vector fields in well, when you have a coordinates on your manifold. The choice of coordinates gives you a canonical basis in the space of in the tangent spaces and in cotangent spaces. So the canonical basis in tangent spaces are denoted by like this. Oh, sorry, I probably so I will use I'll use simultaneously a few different notations For instance, you can use just partial derivatives with some indices in the bottom. Or I can use partial derivatives in the usual way. I can also denote them by dx1, dxn. So whatever you prefer, they're all the same. So these partial derivatives represent the canonical basis of a tangent bundle associated with some local coordinate system in M. Okay. Now, if you have a polyvector field and a p-vector field, so I'll denote the p-vector fields by T sub p poly of M. And a differential form phi of degree p on M. Then you can consider their pairing, alpha and phi. So to this end, you just actually I'll expand this formula. I've abbreviated to just Ti, okay? And here you have some phi j dxj. And then, of course, the pairing of this basis element and this basis element is equal to delta ij times the sign of the permutation.
So basically the number of times you permute those.
Yeah, more or less. Just let me see. Is it necessary to introduce this sign here? I'm not sure about this. Actually, it is easier to give an example than to look for the formula. It's something like this. You have, say, alpha d1, d2, and phi dx1, dx2. Right? So in this case, you just obtain alpha times phi, right? And then you take d2 and let it go across x1, and then couple, and then you pair it with dx2 and get just 1. So it's just minus alpha phi, right? Just something. So actually, sign is actually necessary, but it is easier to explain in an example how the sign appears than to give it a precise definition in terms of the number of permutations and so on. It's really a nightmare, these signs. In any case, we have a natural pairing. Natural pairing. Okay, what do we do further? Next step is to consider bivector phi in the space of sections of the exterior square of tangent bundle of M, and let f g be two functions. Then, of course, what we can do is we can pair this pi with the differential form df dg. Take this natural pairing.
Sorry, could you repeat how one evaluates, let's say, the derivative with respect to coordinate 1 with derivative with 2?
I mean,
The differential forms?
it's something like this. When we have identical indices, di, dxi, we just have one. They're just because these are just dual bases, right? This is just basis. So actually, you can write it like this. It's just delta ij, right? Nothing else. Then, but here we don't have just d1, dx1, d2, dx2. We need to take d2 and let it go across dx1. And by general principle, this should earn us the sign. It's actually, actually give the definition in very explicit terms of how the signs appear and why they should appear. That's because we want this pairing to preserve some sort of multiplication on both sides, right? We want to know that when we have alpha, beta on the left and have phi, which psi on the right, then suppose that in this case we want to well, I wouldn't say that only the terms like alpha phi times beta psi will appear in this pairing. Not only they will appear, but they still will appear, right? And we want that these terms, we would like that these terms appear with proper signs on both ends, right? And since we can change the order here and here as well, the signs are actually obligatory. You cannot just omit them. You see? We can change the order here, right? And not change it here. And it will earn us some sign. And this sign should match the sign we have here. So that's why we actually need this sign. But you can just regard this as a kind of definition. That you have this expression, you have this natural pairing on the basis, and then you extend this pairing from the basis to the exterior powers of the basis. Actually, this is done in linear algebra. It is sometimes in linear algebra they just define this pairing in explicit form. They actually use this pairing to define the determinants sometimes. I don't know. Okay, now we have this, and I will denote this by the bracket of f and g sub pi. Now pi is a bivector field, and this bracket needs not be Poisson bracket. In fact, 2 out of 3 conditions we imposed on Poisson bracket holds automatically here. So first, a skew symmetry is evident. That's precisely because of the of this sign condition. And number 2, the Leibniz rule is also holds. So as far as the skew symmetry is concerned, I already explained. As far as the Leibniz rule is concerned, it's actually also quite evident just because the differential on here and here verifies Leibniz rule, and this pairing is linear over the functions. This pairing is linear over the functions.
But this Leibniz rule is not standard.
Standard one. I mean, for f and g are functions. Yeah, nothing else. I don't speak about the graded Leibniz rule.
Okay.
I'm just speaking about the usual Leibniz rule, and since differential functions verifies Leibniz rule in the usual sense, Leibniz rule holds for this pairing as well. Following statement is pretty simple. I don't know if I actually need to prove it. Yeah, they are zero forms. You can phrase it like this. Yeah, we'll very soon have graded Leibniz rule, but At this moment, I'm not interested in this, in the grading. I'm just speaking about the usual Leibniz rule. So a claim is actually that the opposite is also true. If we have a bilinear function, let me call this, if we have a, how do you call this? Let me note it by pi, is a map from C infinity of m tensor square tensor to C infinity of m, which verifies first a skew symmetry and second Leibniz rule, then pi capital is equal to the bracket with respect to pi. The proof is pretty simple. Just freeze one of the argument. For instance, take in local coordinates. Well, coordinates. I don't even care about local coordinates. Okay. F equal to xi. Then we have pi of of xi, comma g from C infinity m to C infinity of m, which verifies the usual Leibniz rule. So this is frozen, right? This is fixed. So we just have a map from functions to functions which verifies the Leibniz rule. Then it means that this function is actually represented by some vector field, right? But the same is true for if we freeze G instead of F. So we just have two vector fields. For both, whenever we freeze X and G. So we have the following expression. It should look like some coefficients, I don't know, xi of f and yi of g, where xi, yi are vector fields. Moreover, since this is skew-symmetric, it follows that this tensor product xi tensor yi is skew-symmetric, sum over I. And hence, it is a section of the second exterior power, this exterior square of the tangent bundle of M. That's precisely the bivector field.
How will you arrive to the tensor product?
Well, when I have this formula, it's precisely the value of tensor product.
Yeah, okay.
It's just this formula. Okay, even more generally, now this is a very simple one, of course, but if you have more generally a map from C infinity of m tensor to the kth power to C infinity of m, which is totally skew-symmetric, is symmetric, and verifies Leibniz rule with respect to any right element, then it is equal to, it is given by the section of the kth exterior power of the tangent bundle of M by the same formula. Okay, and that's more or less it, nothing else. And that's actually the proof that the Jacobi identity will only contain linear terms. Let me return to that proof I gave and discuss the details. So we have some bracket induced by some vector field pi. The question is, when does this bracket verify the Jacobi identity, the only missing part of the Poisson structure? So let us consider the Jacobi identity itself. So for every two functions, for any three functions, f, g, and h, we can take the sum of this form, right? And ask if it is equal to 0. Then, as we did it at the very first lecture, it is easy to prove that this expression on the left is linear. I mean, it verifies Leibniz rule with respect to each of the arguments. Let us denote this expression by j of f, g, h sub pi, and j stands for the Jacobi. So we have Jacobiator of f, g, and h with respect to the bracket induced by pi. And then an easy exercise, or probably the statement, the claim again, is that the Jacobiator is multilinear operator. I mean, verifies Leibniz rule with respect to every argument. GH. So first is symmetric with respect to all permutations. That is to say, when we permute f, g, and h, we earn the sign equal to the sign of the permutation. And it's easy to check, right? There are only 6 permutations of 3 elements, and we just use the Jacobi identity here, the expression and the symmetricity of the bracket to check that the sign we earn is precisely the sign we need. And then also, a bit more complicated but still evident, is the claim that this Jacobiator verifies the Leibniz rule with respect to any of its arguments. Well, from the first part, it follows that if you prove it for some argument, the same will be true for all arguments. I think I've already done this when we spoke about the Jacobi identity at the first lecture. The proof in the general situation is just the same. We only make advantage of the Leibniz rule to cancel out the terms which would involve this, the terms with double Poisson brackets, where both f1 and f2 appear inside the bracket. The terms these terms will cancel out. So I'll skip this, and it follows automatically that the Jacobi identity of FGH is equal to the pairing of certain trivector field with the form df, dg, dh. Right? Nothing else. It is our purpose now to identify this form. In the case when we spoke about the Jacobi identity for the Poisson bracket on the dual space of a Lie algebra, it was easy, right? We just checked the identity by hand, and we saw that what we got was just the usual Jacobi identity for the commutator in Lie algebra. But now here, in the general situation, we need to introduce a bit more notation into the play, because the most natural and most traditional way to identify this trivector field is by introducing an additional structure on vector field, on polyvector fields. So here is the following theorem, which you sometimes call theorem / definition, or definition / theorem. Definition / theorem. For every smooth manifold M, there exists a unique operation bracket on the space of polyvector fields. And denote polyvector fields by the same notation, same symbol T sub poly dot of M. Let me put P here. Tangent with T sub poly Q of M into T sub poly P plus Q minus 1 fields on M. Such that, first, so in case I forget something, I need to take a look in my notices. Okay? I hope you will allow me, because remembering all the signs is quite a horrible thing. Never been able to remember them all by hand, by heart. So first, as you see, this bracket is actually not the usual graded bracket. If some of you have ever seen the definition of graded Lie algebras, then you would probably expect that the degree here would be equal to the sum of P and Q. This is not the case here, because this bracket is actually degree minus 1 operation. It does not send the elements of degree P plus Q to the elements of degree P plus Q. It sends them to P plus Q minus 1. And therefore, all these graded identities, which you might have already seen in some other courses, will be a little bit different. So I'll try to reproduce them accurately. So first we have a skew symmetry, the graded skew symmetry. Graded skew symmetry. That is to say, if you have a P field alpha and a Q field beta, and the bracket of beta and alpha will differ by the sign equal to -1 to the power P minus 1, Q minus 1, times Q minus 1, and minus in front of it. Right? That's the first. Now the condition number 2. Is equal to what? Graded Leibniz rule. Now we have the graded Leibniz rule, which already implied it. Yeah, graded Leibniz rule.
Here we should alpha p. That is p and q are the degrees.
Yes, P and Q are their degrees. Whenever I use these subscripts, or superscripts, probably better to say superscripts, these superscripts denote the degrees. So here it is. The graded Leibniz rule, it is like this. So, I forgot to say, but I think everybody knows that just like in case of differential forms, you can introduce the wedge product on polyvectors, right? When you have two differential forms, you can form their wedge product, and the same goes with the same can be applied to polyvector fields. You can form their wedge product. And this wedge product is skew symmetric in the usual sense. I think everybody knows how to write down the formula. But how to write down the formula for the graded Leibniz rule is a little bit trickier because you need to take into consideration the signs. Okay, so you have P, B, Q, and C, R. So what you have here is first A, B, C. So no sign emerges here, but then we need to introduce sign in the second term. -1 to the power Q times P minus 1, B, A, Q, P, C, R. I hope I haven't made any mistake here. So that's number 2, the condition number 2. Now the condition number 3. You can call this condition yeah, so let's put the important conditions first. The graded Jacobi identity. Graded Jacobi. Again, this graded Jacobi is with respect to the degree -1 brackets, so it's a little bit different from what you might have seen. I think I better write it down again. So it looks like this. The symmetric way to write it down is like this. You take A to the A of degree P, B to the of degree Q, and C of degree R. Then you need to introduce sign here already. So it's -1 to the degree P minus 1, R minus 1, right? Then, fortunately, this sign will be very regular. So if you rotate it, you put B in front, A on the end and C in the middle, and just again, the sign will be equal to -1 to the power q minus 1 times p minus 1. So you take the elements on both ends and take their signs. And finally, -1 to the power r minus 1 times q minus 1 cr a p b q. And that should be equal to 0. So these are 3 conditions. But it's not enough to define the brackets, because we need to introduce what they call the normalizing conditions. So this normalizing conditions actually prescribe the value of this bracket on the polyvector fields in low dimensions. So let me write down these conditions all together. First of all, if you work with 0-degree forms, 0-degree vector fields, then their bracket is equal to 0. And that's actually quite natural, because they have 0 degrees, so their bracket should be of -1 degree, and there is nothing in -1 degree. Nothing we can do. Then if you take a vector field x and a function f, what you get is again what you can expect. F is a 0-degree form, 0-degree vector field, right? And x is a degree 1 vector field, right? So the bracket should be of degree 0, and that should be a function. So up to the sign, we have a unique function, naturally associated with a function in the vector field, just the value of vector field on this function. And third condition is when you take x and y to be just vector fields, then you get just the usual commutator. So this is the, finally, a theorem. Now, the proof of this theorem is very straightforward, and I admit it. The proof is very straightforward in the sense that every polyvector field alpha can be written down, as I explained, in the form of the sum alpha I times dxi, dx1, dxi1, dxip, right? You can rewrite it, well, not in a unique way, but in some certain way, as the sum of x1, xp. And the sum is taken for I from 1 to a certain index n. So just take the wedge product. Every polyvector field is a sum of some wedge products of usual vector fields. It is not unique. This decomposition is not unique. Therefore, you cannot just use the formula I'm going to write down as the definition. But then, if you have two such expressions, say x and y's, right? And you have this, and you take the commutator of this, and from 1 to m, y1, j, h, y, q, j. Then you use we created Leibniz rule, and this definition to check that you have a unique way to write down the right-hand side. Actually, it will be equal to sum with certain signs of xi commutated with by j, which all the rest. Right? So this formula, if it exists, is unique. Then you need to check that this formula is well defined. To this end, you need to check that if you change the order of xi's in this expression and change the way you define these xi's, and there is only one thing you need to check, that if you have x f wedge x1 wedge x2, this of course is equal to x1 wedge f x2, you need to check that you get the same result from both these and these sides. Right? So, so it is well defined. If you check it and you do it correctly, then it is well defined. Right? It verifies this condition automatically. Right? It verifies Leibniz rule automatically. You can check it and it verifies the cobidentity automatically. And you are done. So this bracket is the well-known Schouten-Nyquist bracket. And there exist explicit formulas for this Schouten-Nyquist bracket in coordinates. I think one of our exercises for next time will be to prove the formula in some particular case in coordinates, which is not very easy. You need to deal with indices, pretty wide set of indices. What is the purpose for us to introduce this bracket? So let me again spell for you the name of this bracket. This bracket is called Schouten bracket, or the Schouten-Nyquist bracket. I don't remember who of these Dutch guys was disciple and who was the teacher, but they were related like this. Schouten-Nyquist. I think Nyquist was the teacher, but I'm not sure.
But isn't this a Gersten-Haber algebra?
It is. It's actually, I'll speak about this at this seminar, but not today. Not today. Okay. Schouten-Nyquist bracket. It's one of the multiple brackets you can introduce on these algebraic structures associated with manifolds. There are also so-called Fröhlicher-Nyquist brackets, Richardson somebody's brackets. They all come in pairs. There are also some brackets introduced by Vinogradov, some brackets introduced by Magritte and others, and there are lots of them, and they're quite interesting to study. I mean, these algebraic structures associated with smooth manifolds are quite interesting. They contain lots of information, but it is hard to derive this information from these algebraic structures. So what was the purpose for us to introduce this Schouten-Nyquist bracket right now? It is the following theorem, which I am going to prove today, at least to sketch the proof. Maybe I'll give some details next time. Theorem. Let J sub P F G H be the cobiator, and as I told you, it is equal to some trivector field paired with df wedge dg wedge dh. In that case, gamma p, gamma sub pi, should be equal to the Schouten bracket of pi with itself. In particular, pi defines a Poisson bracket if and only if its Schouten bracket with itself vanishes identically. So, modulo this theorem, we can say that a Poisson structure on a smooth manifold is a choice of a bivector field, verifying this equation. You can rewrite the definition. Poisson structure on M is the choice of pi, a two-vector field on M, which verifies the condition pi with itself vanishes identically. I would love you to to consider to do the following exercise. Suppose F be a map from a manifold M with Poisson structure pi M to the Poisson manifold N with Poisson structure pi N. I explain what would it mean that this F intertwines Poisson structures in terms of the Poisson bracket. What does it mean? But now the question is how to write down this condition in terms of Poisson bivector. What does it mean? So now I'm going to prove this theorem, and I'll do this again, not in full details probably, but still with some details. And the quantity of details I'm going to give depends in a large, in a big deal on the quantity of time I still have. How much time do I have? It's up, yeah, right? Okay, then I will be very sketchy, but still, but I still give some. And next time we'll discuss the details. So proof, and this proof is based on the following formula, which is due to Andrei Lichnerovitsch. Lichnerovitsch formula. Formula is as follows. Suppose you have a differential form omega. So I used to write differential forms on the right in the when I paired them with Polyvector fields, but it's, I don't know, maybe it's more convenient to write it on the left. It doesn't matter much, but I don't want to spend time trying to change the order. Not very important. So P and Q are Polyvector fields. So they are polyvectors of degrees P and degree Q on M. And now the Lichnerovitch formula identifies the Schouten bracket of P and Q in terms of natural operations that you have on differential forms. And here is the formula. So first term is minus 1 to the power P minus 1, Q minus 1, now we have this. The Darboux differential I sub q of omega. I'll explain what it means. Times p plus or minus the Darboux differential I sub p of omega paired with q. And finally, minus 1 to the power p dp d omega p hq. So you see, the only thing which probably remains to be explained is this term, this expression. So this expression actually denotes the contraction of differential forms with respect to polyvectors. We all are used to contractions of differential forms with respect to vector fields. But now you have a polyvector, and polyvector is just a wedge product, as I explained, xp. Then you can take the contraction of omega with respect to this in the usual sense, just by iterating contractions first with x1, xp, then with xp minus 1, and so on. So just the iterated convolution, iterated contraction of omega and coefficients of the polyvector fields. Okay, so I'll postpone the proof of this formula to next time probably, or maybe we'll do this today at our exercise session, I don't know, it's up to you. Let me now prove the claim of this theorem modulo this formula. Suppose we want to prove that gamma sub pi, so the cobidentity, right? The cobidentity of f g h sub pi is equal to 0 if and only if pi comma pi is equal to 0, right? So what we do,
Here, what is omega is any form?
is any so yeah, sorry, omega is a p plus q minus 1 form. So that this pairing is well defined. Yeah. So as I explained, this is equal to the pairing of the form df, dq, dg, which dh, right, with some pi, right? And now we need to prove that this is equal to this. To this end, I just expand this, substitute it here, and expand the right-hand side using the Lichnerovitsch formula, right? So first of all, the first term is, so p is equal to 1, p is equal to 2 and q is equal to 2. So here we have minus 1 to the power 1. It is just minus. And what we have further is the differential of I sub p, I sub pi, omega. Further, what do we have? what do we have? Is, sorry, pi, right? That's the first term. The second term is again minus. So what we have here, minus 2, like this. Right? Now this term vanishes identically because the omega is equal to 0. Omega is df dg dh, so the omega is equal to 0. So we continue. So up to this minus 2 in front. We have what is I sub pi of omega? It is this. You take a differential of the following sum. So first you contract pi with the f dg, right? And this is just the bracket of f and g sub pi wedge dh. Then, if you permute dg and dh, you get minus the bracket of f and h wedge dg. And finally, if you permute df dg, df with dg and dh, you get plus again g h wedge df. Here it is. And you pair it with pi. So what you get is minus 2 in front, but inside what you have is, so d cannot be applied to this term or this term or this term. D only applies to the bracket. And when we have d of the bracket and pair it with pi, we get the Poisson bracket again. So what we have is the double Poisson bracket of f g comma h plus or minus Poisson bracket of f and h comma g and plus g and h comma f, and that is precisely the equilibrator. So up to this, I made some kind of mistake. I thought that gamma is exactly equal to the commutator, right? To the Schouten bracket of pi with itself. But in fact, gamma sub pi is equal to minus 1/2 of pi on pi. But that's not a very big deal, of course, right? Since 1/2 is a constant, there is not a problem. Okay, so modulo this Lichnerovitch formula, the theorem is proved